In this series, we breadboarded the entire Atari Breakout arcade game to both learn this unique circuitry and to validate changes required to swap out old 9000 series TTL. After breadboarding each section, we added it to our retro schematic in KiCad. Today we'll start designing the circuit board per those schematics. Now I'd love to just start throwing down parts and traces, but in this instance, a little advanced planning will save us tons of headaches. Like I mentioned before, this is not a KiCad tutorial. I'm the one that needs the tutorials. Before we get to that PCB, we need to firm up our design parameters, like the stack up, spacing, and grid. We're also going to need to clean up our footprints, finalize our power options, and add any extras like debug headers and blinking lights. When we're finally ready, we'll instantiate the parts and route. For the design parameters, we're going to stick with the basics and make it straightforward and boring. I'm using JLC, so we need to adhere to their manufacturing specs. And naturally, you'll need to assure that the design parameters comply with your preferred board house. You can see the JLC specs simply by clicking on Capabilities, then selecting the product type. We can set a lot of these constraints into KiCad, and it will use those during EDM checks. Naturally, we'll set our parameters more conservative than the JLC limits and adjust if necessary. For our stack, we're going with a 4-layer board with the inner ground plane nearest the components. This will allow us to make the board smaller and more rigid, beef up power distribution, and improve signal integrity, which may not be a good thing in this design. We'll also need to keep a standard 62mm or 1.6mm overall thickness to fit the card edge connector. As much as possible, we'll align components on a 100mm grid. We'll go with 12mm traces and 13mm spacing. This dictates a nominal 62mm pad, so we'll use that in most instances. Naturally, some parts will require larger pads, so this is just a general framework. 12mm traces with 13mm spacing also allows us to run traces on 25mm centers. If we look at density, the original had a maximum 15 vertical tracks and 8 horizontal tracks outside the ICs. We'll keep this track density, and with our spacing, we should be able to shrink the board a bit. The original was pretty big at 11.5 by 16 inches, so this is one case where a little shrinkage is okay. Since we have 8, 14, and 16 pin ICs, we'll align these packages east to pin 1 just like in the original. We're adding decoupling capacitors for each IC, and to keep compliance with our component grid, these will be 200 mils east of pin 1. To fit those vertical tracks, we'll need a minimum 1.2-inch chip-to-chip column spacing. The original board has 1.6-inch column spacing, so that should save us about 3 inches of board width. To fit those horizontal traces, we'll need a minimum of 0.6 inches between rows. The original board has 0.8 row spacing, so this should save us over 2 inches of height. I do want to add debug headers in many locations that will reduce channels, and vias will also limit channel runs. I think we'll start with this chip spacing and see how it goes. There is a little extra space down the middle for those ceramic disc decoupling caps. I think we'll also keep extra space in the middle, but use it for our distributed VCC filters. Keeping these parameters in mind, I went in and adjusted all of our custom footprints. I also made sure that each component has silkscreen data on both sides so we can more easily identify locations. I created this card edge connector from the manufacturer's specs. Then I drew up a test schematic with one component of each unique footprint and created a test board from that. I verified everything looks nominal, including the 3D models. We're almost ready to throw down parts, but we need to make some schematic adjustments for power and extras first. There are several ways to power this depending on your use case, and I made adjustments to sheet 4 for this. For a pure in-cabinet replacement, The main board receives 16.5 volts AC through connector pin pairs C3 and D4. This is rectified by CR1 and CR2, filtered, fed into a 5-volt regulator, and distributed to the logic. The post-rectified DC is also used to power the LM3D amp. With low-powered Schottky, we need less than 2 amps, but we will go modern here and eliminate the need for a heatsink by using a PSU5 switching replacement like we used in part 3.5. If you're just using the control board or plan to roll something else, there are a few other ways to power this. We can feed 12 volts DC into the control board, which simply feeds 12 volts DC directly into all 4 AC pins. We'll also add an onboard barrel connector for 12 volts DC in case you're not using the control board to feed. Everything else on the main board in this configuration stays the same. If you never plan on plugging this into a cabinet, then you can jumper out those 2 rectifiers. I suppose you could run this in cabinet using a 12 volt DC brick instead of the AC feed. Just leave out those rectifiers to bypass the AC. Another way to power this is by pumping 5 volts DC directly into the logic. In this case, we don't need the rectifiers or 5 volt regulator, and I added a barrel jack for this. In this setup, if you're just using the audio line out and don't need the amp, no other power is required. If you need the amp, then you'll still need to supply 12 volts DC via a small 1 amp adapter. Just a few notes here. I changed out the old rectifiers for 1N5400s, which handle more current so they'll run cooler. I also added CR101 to the amp supply line to segregate it for better noise immunity. You'll notice the convention of using site names above 100 for any part we add beyond the original design. For this section, I added the 2 power input jacks, 2 power supply indicators, and VCC filters that will spread throughout the board. When we started this project, I said we'd add debug headers for interesting signals. I placed these on sheet 5, which we added to hold stuff beyond the original design. I added headers for all counters and for other interesting signals. You don't need to populate the headers, but they will be available. In each header, you'll see that I used pin 1 for VCC and pin 8 for ground. The ground makes a convenient probe reference, and VCC is available if you want to plug on widgets like LEDs or digit displays. I was careful to place counter-type outputs on the same pins so a single display widget design can be used for any counter-type header. You can see I added headers for the oscillator divider, sync latch, video counters, ball counters, etc. I also added a header with all of the ball bias lines so we can make a ball motion meatball display widget for this. Next, we have the UI counter for external video like the RGB to HDMI adapter from part 16. And I added both the main card edge connector and the optional 25-pin header that you can use if you don't want to buy the 44-pin edge connector for the control card. That 25-pin header is also a convenient way to probe the I/O signals. The original has no onboard indicators, so I wanted to add at least a few LEDs like we did on the breadboard. We already added them for the power supply, and I added LEDs for run state, attract mode, endgame level, and the 2-player game condition line. These are interesting signals that are not shown either on the control card or on the screen. If you remember on the control card, we added a button that lightly pulled up the external antenna line to trigger a reset. I also added onboard buttons to conveniently set and reset the operational latch. We have 2 coin switches on the control card, but I think we should also have the ability to add credits directly on the main board. After poking around a bit, I discovered that I can trigger a coin drop by pulling one of the stage B reset lines low, which raises the inverted Q output and properly triggers the next stage. Since the Q output is forced on, the coin lines stay high, so this button will not set the operational latch. You'll need to set that first before dropping coins with this button. Best I could do without any serious logic changes. You don't have to install any of the extra headers, LEDs, or switches, but for this coin switch, you'll need to install the separate pull-up resistor. Also remember that for any unused coin switch, you'll still need to tie the NC input to ground, and I may add onboard jumpers for this, don't know. I added notes to the bottom of sheet 5 as well. There are a few reference collisions on the original schematics with capacitors C1 through C9 and chip sites C1 through C9. I kept the chip references for consistency and renamed capacitors C2, 3, and 4 to C92, 3, and 4. Capacitor C1 is replaced by additional electrolytics spread throughout the board, and capacitors C5 through 9 are replaced by decoupling caps for each IC. I think we're done with modifications, and none of these violate the intent of the original logic. Before instantiating parts, I ran the rules checker and cleaned up any issues. Let's switch to board view. Turn off the frame and rat's nest display for now, and update the board from the schematic. This should be interesting. Well, wow, that's going to take a lot of rearranging. Instead of moving everything by hand, I created a script to at least move the ICs, associated decoupling caps, and any related debug headers automatically. This will save a lot of time and we'll move the rest by hand. Okay, I finished moving parts around close to the original layout but more compact. You can see the original 11.5 by 16-inch board outline and my proposed compact outline. Hopefully we can route everything in this space. I did make a couple of changes as I was moving stuff around. In the power supply, I swapped out the PSU5 for a PSU5A, which is simply the same 5-volt 3-amp regulator but in a TO220 package, which will save us board space. I also swapped out the main axial filter with a radial one. We can downsize here because we're drawing less current, and these PSU5s only require that we keep the input ripple above the 7-volt mark. Remember that you only need the filter and diodes if you're dropping this in a cabinet, and you'll need that 5-volt regulator if you're using the cabinet's 16.5-volt AC feed or a 12-volt DC brick. If you're using a 5-volt brick, the rectifiers, main filter, and regulator are not required. And if you're only ever supplying 12 volts DC through the control card, you can either keep those rectifiers or you can jumper them out if you never plan on putting this in a cabinet. I also added onboard footprints for audio and video jacks for convenience if you're not dropping this in a cabinet or using the jacks on the control card. Since we had trouble with the availability of the 7-segment decoder, I modified the Jack 5 footprint to accommodate both real 7448s or a 20-pin 16 Victor 8 type PLD. These microchip ATF 16 Victor 8Bs are just over $1 American, so it's a cheap alternative if you have a burner. I wrote a CUPL script that takes the 5 used input lines and produces the correct 7-segment data. We don't need to implement the unused pins in this case, and there's no room in these parts anyway. I horked up one for the breadboard, and it works like a charm, actually better than the real part. The last major thing I did was to abuse one of the spare sites to add RGB to HDMI support directly on board using another PLD. This replaces the 5 discrete chips we use to breadboard our support circuit. I think this is a reasonable solution for adding color. I'll drop the source and output files for both of these PLDs into GitHub for your abuse. Let's remove the legacy board outline. Add the VCC and ground power planes. Turn on the rat's nest. Ooh, fun. And start routing. Wire up the oscillator and clock divider. We'll route the clock line first so it has the cleanest path. I think I'll just shut up and route the rest. Well, that was fun. The rules checker is clean. Generate the Gerbers and drill file. I checked the outputs using the built-in Gerber viewer. And also ran them through an external viewer. This one's pretty nice. Zip those up and drop onto JLC. Okay price on a per board basis. Alright, we've got some time before getting those back. I won't push any of the KiCad or CAM files until after we're sure we got a clean working set, so hang in there. Thanks for watching.